Good evening. Welcome to the third of these quarterly lectures in this new series we call the Frontiers of Cosmology. So my name is John Richardson. I'm one of the professors in the Physics and Astronomy department here at UCR and one of the organizers of these events. So this event is being organized tonight and in the future will be organized by a new center at UCR that is forming that we call the Center for Experimental Cosmology and Instrumentation. This is an exciting new effort scientifically that is being led by one of the most preeminent physicists in the world, a 2017 Nobel Laureate in physics and recipient of the 2023 National Medal of Science, Professor Barish, professor here in the Physics and Astronomy department at UCR. And you'll hear from him directly later tonight. And the aim of this new center is to create new technological innovations that will enable the next generation of cosmological measurements to answer some of the deepest questions about the origin, the evolution of the universe. And so if you're so able, we would like to ask that you consider supporting this new center in any way that you can. This will allow us, for one, to keep these types of public events free, and it will also hugely benefit UC Riverside students from undergrad to grad level, even postdocs, and it will support some of the world-shaping research that's going to be carried out here. So one announcement is that after the conclusion of tonight's lecture by Professor Michael Turner, we will have a short question and answer session. So we ask that you please keep your seats after the talk is over, and we will have time for a few questions. So with that, I would like to introduce the Dean of UCR's College of Natural and Agricultural Sciences, Professor Peter Atkinson.
Wow, what a crowd. I gave a job interview here a few months ago, and I can tell you this is much larger for a very good reason. Science matters. Let's keep that thought. You're all here because you're going to hear about science, and it's fantastic to see such a full room. Science matters, and you're going to hear some great science this evening. I'm here to introduce Barry. John's already done that. He's somebody who needs no introduction. But I am delighted at the impact that he's had on our physics and astronomy department. The center that John just described is, I think, a phenomenal opportunity for growth in the department and in the college at UCR, and will be a magnet for student scientists to come to UC Riverside, to the Inland Empire, and do great science. This is exactly what we should be doing. I will say without any fear that of somebody coming after me that I point to the other 12 departments in CNAS and say, this is what you should be doing. You should be following physics example in terms of doing this outreach, doing these types of seminars, and dreaming big about the impacts that your own discipline can be doing for our campus, college, and region. This is a great example of the future and how we will achieve it and seize the moment to show what science is really about and the impacts on society that it achieves. So without that, I'll introduce Barry, who, as I say, needs no introduction at all.
Thanks. Hi. So first, let me just mention that so far we have, in addition to myself, we have 3 young faculty in this effort that's sponsoring this program. You just saw John Richardson, who works in gravitational physics. And second one somewhere here is Sean Westerdale, wherever he is. And the third one is Steve Choi. And they cover different areas of what we are trying to do, which is to work in one of the forefront areas of physics and astronomy, in experimental cosmology, or areas in that general area, and to develop the forefront technologies that can make the next generation do the kinds of science that we think is waiting for us to do, and involves a lot of big instruments on the outside. So the idea here is that we're building or developing the kind of instrumentation that'll enable building big instruments that you read about and are done not on campus here, but are done in various places. My job now is to introduce the speaker, who's Michael Turner, down here. We'll talk in a minute. He was a undergraduate at Caltech, my original institution. And actually, he started at Caltech as a freshman when I was a very junior faculty at Caltech. And he happened to become my advisee, or he says I was his advisee. I'm not sure which. But anyway, I've known Michael since he was a lowly freshman starting Caltech at a time when Caltech had just admitted women. And so this was a while ago. He then went on after he graduated from Caltech to Stanford University, where he got his PhD. And from there, he went to the University of Chicago, where he spent essentially his whole career. While in Chicago, nearby is the big particle physics laboratory called Fermilab. And he became connected then to Fermilab in addition to being a professor at University of Chicago. And he and his colleagues started an effort at Fermilab in astrophysics, the kind of fields that we're talking about here today. And that has become a very important part of the big laboratory at Fermilab. At Chicago, he also created, or was part of creating a big institution, the kind of thing we have aspirations to do here. He was the director of the Kavli Center for Cosmological Physics, I guess, and was the director of that for about 10 years, from 2010 to, I think, 2020 or 2019. He's gotten many awards. He's a very famous scientist. But just to name a couple, he got an important award from the National Academy he's a member of the National Academy of Sciences. He won something called the Heinemann Prize for astrophysics, his field. He got the Lilienfeld Prize from the American Physical Society and many others. At the present time, he's co-chair of a National Academy study on the future of the field in elementary particle physics, and I work for him on that, being a member of that committee. And that soon will have a report which is presumably going to help plot the future of that kind of field. So it's a big responsibility to kind of give the direction of a fundamental field in physics or astronomy. With that introduction, let me hand the mic over and the talk over to Michael, and he'll give his talk.
All right. I think I got the two questions. The button here says push, so if something bad happens in the room, let's see if that,
A little lights blinking.
it's blinking. Is that good?
Yeah.
Okay, then I'll get this. No, can you hear me? There's a light blinking, and it says 30, 29, 28, 27, 26, 25, 24. It's on 10, and it just hit 9. How's that? Is that working? I can hear me. Well, I could start with this microphone. Let's see if we can get the other one fixed. Oh, I get to see the talk up here. I'm going to talk about the universe tonight. And oh my God, you have until midnight, right? There's so much to say. So I divided this into what we know. And so that part is stuff we know for sure. It's not going away. That's what we know, and that's really amazing. And then, so what we know is really cool, but for the younger people in the audience, the big mysteries is what is most interesting, because you don't want to go into a field. You don't want to, you want to know that there's something for you to do. And so the big mysteries and how we will find out, I was told by Barry I had to put that in, that this is because of instrumentation. And but science, particularly physics, is all about not how you want the universe to work, but how it actually works. And so you can have the greatest ideas, and I'll tell you some really big ideas, but you have to test them to find out if that's really the way it is. That's the brand of science. Oh, turn this one off. So apparently, how's that? Does that work? Really? Okay, so I can turn this one off.
Try to increase the volume on the.
Okay, they're going to increase the volume, and that one's still ticking over there, so I would. Is this, do you think it's working? Should I turn the microphone on? It is working? You know, it was funny, when I was undergraduate, he could never hear me. You know, I would try to tell him my ideas, and he said it's not getting through. But so can you hear me in the back? Oh, so it's working. Okay, good. So I'm done with this one. Great. Okay, well, let's get on to the good stuff. Oh, but now, oh, I see. Now the slides aren't moving. Did I do something here? Something I said? Oh, I am not. Oh, I see. No, I don't see. Ah, great. And actually, do we have more light than we need? Because this isn't Chicago. In Chicago, you'd want to keep the lights up so to make sure that no one's like stealing your stuff. But this is California, so we can, because I want you to be able to see these slides. So part one, oh yeah, that's good. Is everybody still comfortable? Okay, good. What we know for sure. And we'll, oh, I see. This is going to be a little slow. This is a big slide deck. So we know for sure the universe is really, really big. And how big? 200 billion galaxies. Does everybody know what a galaxy is? So our galaxy is the Milky Way, and a galaxy, each galaxy has about 100 billion stars. And oh, it's really, really big. It's about 30 billion light years across. Does everyone know what a light year is? That's, oh boy, these people are really, so if you don't, there's plenty of people who do know. So if you don't know, just turn to the person next to you. So that's how far light can travel in a year. Is it 10 trillion kilometers or something like that? It's really big. So, and the universe, it's big and old. It's about 13.8 billion years old. And does everybody know what this picture is? The James Webb Space Telescope took that picture. Let me show it to you a little better. That is 1/30 millionth of the universe. So it's a tiny, tiny little bit of the sky. How do you know it's a tiny little bit of the sky? The only stars that you can see, there's maybe 10 stars in there. And there's about, if you count them, each one of these fuzzy things, so the stars, you might say, how come the stars look funny? They're so bright in the James Webb Space Telescope that the light reflects off of the infrastructure of the telescope and creates those spikes. But the galaxies, there are about 10,000 galaxies, those little smudgy things. And that's 1/30 millionth of the sky. And I bet a lot of people are good at multiplication. And so if that's 1/30 millionth of the sky and there are 10,000 galaxies, that means there's 300 billion galaxies, each with 100 billion stars. You keeping up with me? Yeah, okay, good. Can I speed up? Okay, better speed up here. This is another one. The Webb telescope is absolutely amazing. And have you all seen these images? So this is a fun image from a slightly different part of the sky that has a galaxy that looks just like ours. It's not very nearby. It's not our galaxy. We can't take a picture of our own galaxy. But we live in a spiral galaxy, and it looks like this. There are a couple 100 billion stars in our galaxy. So the light from galaxies is just from all the stars in them. And oh, here's, this is a picture of some stars. Actually, this is a Hubble picture. And so this is our own galaxy. And this is a picture of the nearest star, Proxima Centauri. It's about 4 light years away, or about 40 trillion kilometers for what it's worth. So there are a lot of stars out there. Oh, there are a lot of planets. So how many planets are there in our solar system? How many people say 8? How many people say 9? So you can tell the age by the number of planets. But most stars have planets around them. And so this is a catalog. This is old. It's probably a few years old. Thousands of planets around other stars. And remember how many stars in 100 billion stars in our galaxy, 100 billion galaxies. That's 10 to the 22 galaxies. And so there's a lot of exoplanets out there. Well, they're called exoplanets. And oh, I think I have another. They're so boring. Well, compared to what we're going to talk about. And so there are other solar systems out there. Here's our solar system. And the TRAPPIST-1 is, actually, it's a little smaller than our solar system. But yeah, there's other solar systems out there. Enough of that. So the universe is really, really big. And we'll get back to exactly how big is it? Because I just showed you the part that we can see. So are there parts that we can't see? So I'm planning some questions here. So the universe began, I bet people know this, from a hot Big Bang. How many people know that? Okay, I can race through that. But this is a required part of my talk. So this was discovered roughly 100 years ago. I kind of remember it. Barry probably remembers it too. But this is kind of amazing, at least for the senior citizens in the audience. 100 years ago, we knew of only one galaxy. One galaxy. And 100 years ago, this person, Edwin Hubble, showed that these smudgy little things, they were not as easy to see with the telescopes at the time, actually had stars in them and were galaxies. And his discovery in 1924 enlarged the universe by a factor of 100 billion. So we're going to get to the end, is how big is the universe? And well, we know there's about 300 billion galaxies in it, but he's the guy who found that there were other galaxies. And the galaxies are separated by millions of light years. So that's Hubble. And then he did something else. And don't tell me he built a space telescope. It was named after him. So the other thing he did was he discovered that the universe was expanding. And oh, he's on the cover of Time magazine. So science is really important. Science does matter. And so here's that same picture. And so what he found is that the galaxies are moving away from us, all the galaxies he could measure. And the ones that are farther away are moving faster. So that's got a bigger arrow. And so the implication of this measurement is that the universe began from a Big Bang. And so let me take away the galaxies because they're interfering with your thinking. So he saw this pattern. And so that pattern kind of looks like, well, if we shrink this pattern of motion down, if we just say those galaxies, where were they a long time ago? Well, we move them all backwards. And if we go 10 billion years, if we go 14 billion years ago, they'd all be in the same place. Now, this is not the best way to understand the Big Bang because it leads to a question that you can ask me later on. Are we at the center of the universe? And this is not Harvard, but at Harvard, everyone's at the center of their universe. But we're not at Harvard, so that's not the right answer. But you can kind of see how this works. Is suppose you had an explosion here 14 billion years ago, and we look at it 14 billion years later, the pieces that came out of that explosion that are moving faster will be farther away from the center. Now, that's not really how it worked. It wasn't an explosion into space. It was actually an explosion of space. And Einstein set us straight on that, but you can ask me that later. But there was a Big Bang, and it was Hubble discovering this pattern of motion that clued us into it. And this is a required part of my talk. So he got all his degrees from the University of Chicago. And not only that, this is March Madness time, right? Okay, so he was on the University of Chicago 3 years running, won the NCAA basketball tournament. That is a true fact, as opposed to an alternative fact. This is a picture. He was the power forward. That's him, Edwin Hubble. And you can Google it, but not while I'm talking. So you know about the Hubble Space Telescope, named after Hubble. So here's one of his basketballs. And do you know where this is sitting? Space Shuttle. And this was on the final servicing mission of the Hubble Space Telescope, and we sent the basketball up. So who is we? We got more University of Chicago here. So the Hubble repairman, now you have to be old enough to remember Obama. I think he was the president after Lincoln, but I'm not quite sure. And he had he loved science. And he had a big science event on the White House lawn, and they had telescopes and everything. And he introduced John Grunsfeld. Oh, he's a University of Chicago graduate, as the Hubble repairman. And there he is repairing the Hubble. And he's the one who took the basketball up there. And I got to tell a story. So did you know you can get email from the shuttle or from the space station? Did you know that? So we sent this up. The story about it going up is long and complicated. I get this email from the space shuttle with this picture while he was up there. I didn't even know what email was, but I opened it anyway. Okay, there we go. The hot part. So we're speeding up. We're all the way up to 1964. Then we'll get to the present pretty soon. So the hot part of the Big Bang. So you saw the Big Bang. The Big Bang is just that the universe had a beginning. And the hot part was 1964. These two gentlemen, Arno Penzias and Robert Wilson, scientists again, working at Bell Laboratories, and they discovered some mysterious microwaves. And this is a really good lesson in science. They were not looking for these mysterious microwaves, and they were worried about what they were, and they weren't going to dismiss it as, oh, it's just some noise, random noise, just keep doing what you want to do. So they noticed that the antenna was a pigeon roost, and there was a white dielectric substance associated with pigeons in the antenna that they thought might be responsible for the noise. Oh, some of the time I ought to stand over here, right? And so they scrubbed it out and it didn't go away. And what they discovered is the universe is filled with microwaves. The kind of microwaves that are given off by an object at about 3 degrees above absolute zero. So every object, by virtue of its temperature, gives off a certain kind of light. So you've seen, actually, does anyone know what an incandescent light bulb is? So the filament is hot. It's about 5,000 degrees. It gives off light. So something that's cooler gives off something that's redder. And so something really cool gives off microwaves. Okay, so the universe has a temperature of about 3 degrees. Actually, it never gets down to 3 degrees around here, so you wouldn't know that anyway. The difference between absolute zero and Fahrenheit, but it's absolute zero. So that's a very boring number, but as the universe expands, the temperature decreases. And so that gets even more boring. But if you run the movie backwards, that means that in the beginning, and I'm going to use a technical term here, it was hotter than hell. So it was a hot Big Bang. And that changes the whole way that we think about the universe. And so here's a little picture of what we know about the universe. So that means in the beginning, it was really hot. And when you heat things up, imagine you're heating up water. So you heat it up, it evaporates, it becomes a gas. You heat it up some more, the atoms get torn apart, it becomes ionized. And if you heat it up hot enough, you reduce it to the neutrons and protons in it to their quark constituents. And so what this means is when the universe began, it was a soup of elementary particles. So file that away in your head. Cosmology and elementary particles. So we'll come back to that. And so this is what we know about the universe. It began as quark soup when it was about 1/100,000th of a second, or 10 to the minus 5 seconds old. The quarks, which make up neutrons and protons, turned into neutrons and protons. It was cool enough so that neutrons and protons could form. When the universe was seconds old, it was cool enough so that neutrons and protons could combine and form nuclei. And they made helium, a little bit of lithium, and some deuterium. And then the universe is expanding, it's cooling, it's slowly building itself up from quark soup. When it's about 400,000 years old, it's cool enough for the nuclei to grab onto electrons and form atoms. Okay, this part is really important, so pay attention to this part. When the atoms form, the universe becomes transparent to light. So ionized matter, if you ionize matter, light can't move very far. And I think the dean has allowed me to do this. I'm going to demonstrate this. We're going to ionize all the matter in this room, and then you won't be able to see me because the light is just bouncing off all the, no, we're not allowed to do that, safety regulations. But I didn't think we had safety regulations anymore. Wasn't there an executive order about that? Anyway, sorry, the universe becomes transparent to light. And so all of this heat of the Big Bang, all of this light of the Big Bang can just come straight to us without bumping into matter. And so these microwaves give us a picture of the universe when it was about 400,000 years old. Oh, and then there's some other things going on here. Gravity starts pulling together matter. I'll talk about that more in a second. Galaxies form when the first galaxies form when the universe is about 500 million years old. Those were the ones you were seeing in the James Webb Space Telescope image. Okay, so I want to focus in on these microwaves. We call it the cosmic microwave background. And it gives us a picture of the universe before there were stars, before there were galaxies. And here's the light. Let's see. So I'm going to go over here. This is today. As I walk that way, I'm going back in time. This is the light from the Big Bang. When the universe is ionized, it's bumping off of electrons, and then the universe becomes neutral, and the light just comes to us. Okay, so we're seeing the universe Before there were stars, before there were galaxies. You ready for this picture? Okay. Oops, there it is. So this is a picture. It's got a couple of things in this picture. Number one, for those of you who are young, you'll be able to instantly know whether you want to be a cosmologist. So if this picture makes your heart go pitter-patter, you're destined to be a cosmologist. If you just look at that and say, that looks like Gaussian random noise, that's nothing. Okay, then you're probably going to do, biology. Okay, so what is the picture of? This is the universe at 380,000 years old. Okay, but it's one of these false color things. So this shows the variation in the intensity of the cosmic microwave background across the sky. So this is the whole sky unwrapped. Yeah, you don't go to class where there's a map on the wall anymore. Do you remember we unwrapped the globe? So it's the whole sky. Where it's red, it's slightly hotter. Where it's blue, it's slightly cooler. And slightly, I mean 0.001%. So tiny variations. Where it's hotter, there's more matter. Where it's cooler, where it's blue, there's less matter. So the universe was slightly lumpy. That is, the density of stuff in the universe, the distribution of the matter in the universe, in some places there was about 0.001% more. In other places, it was 0.001% less. So it was very smooth. But this is the pitch for every time I say instrumentation, you're supposed to give me a $10 bill. This is where instrumentation comes into play, and where one of the young assistant professors that have been hired in this program makes measurements like this. We're able to measure those tiny differences and map out the distribution of matter in the universe. Okay, now I know a lot of you are business students. You want to know about product placement. Everybody know what product placement is? In a movie, they drinking Coke or something like that. Product placement. Do you see the two initials here? SH. Do you see those letters there? Can you see it? You can't see an S here and an H there? Okay, well, anyway, it's the projection equipment here. Stephen Hawking. Product placement. I can see an S and an H. Actually, I'm spending too much time on this already, but if you have a lower resolution of this, it pops right out at you. It's just an artifact. Your eye loves to find features in it. Okay, so it was a hot Big Bang. It was lumpy. Now we come back to economics. Where there's more matter, there's more gravity. And so where the density was greater, the red spots, the matter comes together. And the more the matter comes together, the stronger the gravity, so the rich get richer, the poor get poorer. And so that's what builds up galaxies. These lumps are the seeds that give you the galaxies that we saw in the James Webb. Okay. What's the universe made out of? Okay. There's the answer. So we actually know what the universe is made out of. 5% of it is atoms. So what are atoms? I'm talking about the atoms in the periodic table. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. Oh, I don't know the rest of the periodic table, but okay. Of those atoms, only 0.5% of them, or I should say only 1 in 10 atoms is in a star. So stars represent 0.5% of the universe. So we're seeing the tip of the iceberg when we see the stars. Where are most of the atoms? In hot gas. That's a whole nother story, but they're not in stars. So we can't see them with a telescope. Okay, that's 5%. The other 95% tells you why cosmology is a really exciting field. So 25% is in something that we call dark matter. So you might say, okay, what's dark matter? It's not the periodic table stuff. It's something other than the periodic table, and we don't know what it is, and we're trying to figure out what it is. And it's 25% of the stuff. It produces most of the gravity in the universe. It's the infrastructure of the universe, because the universe was assembled by gravity. And then the other 70% is something even weirder called dark energy. And okay, let me tell you about those two. So how do we know about the dark matter? Because science is about evidence. So in the 1970s, Vera Rubin, there's now a telescope named after her, was studying, this is the Andromeda galaxy. So this is the closest galaxy to us. She was studying the motion of stars around this galaxy. And they go around like planets go around the solar system. And this is their speed. Okay, and so the thing you're supposed to take away, she coined the term flat rotation curve. So rotation, that's the stars going around the galaxy. And it's flat. It doesn't decrease. And if stars were all the gravity, if stars were all the matter, and they provided all the gravity, you don't have to do much calculation to realize that the ones that are really far away, the gravity out there must be weaker. They should be moving more slowly, otherwise they're just going to escape. And so there is matter that we cannot see. We just call it dark matter. And this is an artist's rendition of the dark matter. So here's a galaxy. And the so-called dark matter halo is enormous. So most of the mass of the galaxy is in this big thing made of dark matter. We know it's there because we feel its gravity. Its gravity holds together the galaxy. We don't know what it is. Oh, we know one thing. It's not atoms. It's something new. Okay. What about the dark energy? So dark energy is really weird stuff. So you're supposed to fasten your seatbelts for this part. So in 1998, it was discovered that the universe, the expansion of the universe, is speeding up, not slowing down. So it should be slowing down, right? Because gravity slows things down. But the expansion of the universe, those galaxies with time are moving faster. The universe is expanding faster. That's very weird because they should be slowing down. In fact, for years, people tried to measure how fast is the universe slowing down. And okay, these three gentlemen were involved in discovering that. And they got the Nobel Prize in Physics, I forget what year, 2011, I think. So the universe is speeding up. How can that be? So first of all, gravity can be repulsive. So I see a lot of students here and they're saying, that sure is true. Those problems are really repulsive. No, that's not what I meant. Because if you think about it, the defining feature of gravity is it's attractive, right? I mean, when you think but it can be repulsive. In Einstein's theory, if you have really, really weird stuff, it can be repulsive. And the really, really weird stuff is called dark energy. Okay, so it's really, really weird stuff. It's extraordinarily elastic. The simplest explanation for it is that it's the quantum energy of the vacuum. Okay, you get that? None of us do either. So we don't, so there we go. The universe, 5% atoms. We can't see most of them. We can see, actually I should start with 0.5% stars, and then a bunch of hot gas, 5% stuff we know, 95% we don't have a clue. So is this sounding like there might be room for people to, okay. Quark soup beginning, we already talked about that. But this is just a reminder, this is a big idea. The fact that the universe began as quark soup gave rise to this center that Barry helped start, because there are connections between the quark the very small and the very big. So keep that in mind as we go to what the big mysteries are. And big mystery number one is easy. What is the dark matter? So I'll give you the short list, and then I'll give you the long list later. So we think it's a new particle. And one possibility for the new particle is called an axion. It's a very, very light particle, lighter than the electron. Another possibility for it is a particle called the neutralino. Has everyone heard of superstring theory? So superstring theory makes one really big prediction, that there should be a new particle called the neutralino. So this is, I'm painting with a very broad brush, but neutralino. And then actually, when I made this slide in 1990, we still thought it might be the neutrinos. And since 1990, we figured out how much neutrinos contribute, and they contribute almost as much as stars do. Okay. So very, very light particle. If it exists, it weighs a trillionth of what the electron does. A particle that might weigh 100 or 1,000 times what the proton weighs. And those are our candidates, but we got to test that idea. We want to know what the universe is made of. Oh, I forgot one important thing. These are not particles I invented. So this comes back to this connection between particle physics and cosmology. The particle physicists who work over in this corner over here, they work over in this corner. And their goal is to unify the forces and particles of nature and figure out how all that works. And they said, you know what? I can unify them all if we have these extra particles. And then they hand them to me, the cosmologist, and I go, oh, let's suppose in the quark soup we had axions or neutralinos. Would there be any left today? And you know what the answer is? Yes. And they'd be about the right amount to be the dark matter. So that's what's called, we got Barry giving me the stink eye, that's what's called a beautiful idea. And that's a great story. And I'm good at waving my hands, but you know, beautiful in science, beautiful ideas are killed by ugly experimental facts. So we have to go test that. And, but it is a really beautiful idea, and that's how it should have been done. And so far, the answer is, okay, so we could try to produce these particles at the most powerful accelerator, the Large Hadron Collider. We could try to detect the ones that I showed you our halo. We could try to detect those particles. Or there's another way, these dark matter particles could bump into each other and produce other particles we can detect. And we haven't found them yet. But actually, here's a picture of how you might detect them. So this is in an underground laboratory in Italy. And I'm actually in this picture. I think that's me. And you fill this with xenon. Would have been better if they filled it with argon. You can ask Sean that. Isn't that right? It would have been better if it were argon. Okay. Anyway, it was filled with xenon. And these particles will come through and leave a tiny bit of energy in the xenon. You can detect it and infer their presence. And not yet. Not yet. Very hard experiment. So we don't know what the dark matter is. Oh my goodness, I'm going to quickly go through this one. So when I drew that diagram, we thought we were close to the end. Stars, and then the dark matter particle. So we got one thing left to find, the stars. But now, maybe the story's more complicated, that the dark matter is the only thing we can detect from a whole other world of particles and interactions called the dark sector. Okay, you confused? I don't actually like this story, but it's what all the young theorists are saying. Okay, I'll skip that slide. Okay, how will the universe end? How will the universe end? So that's a big mystery. So I bet many of you on your mother's knee She sat you down, you were like, I don't know, 1 year. When did you hear on your mother? You were 2, maybe? 2, yeah. And she said there was a big bang, the universe expands, gravity slows down the expansion. So this is the size of the universe. We get droopy lines. Am I telling it right? If there's enough gravity in the universe will recollapse, right? And if there isn't enough gravity, if there's not very much matter in the universe, it will eventually stop slowing down. And then there's Goldilocks, the in-between case. And then your mother, you're probably already going to sleep at this time, and said, you know, that determines if in this high density universe, space curves back on itself. Do you remember that part? In the low density universe, it's curved like a saddle. Okay, that's the old story, because including me, everyone was asleep when the mother got to, well, that's a simple story. But if we put in dark energy, first of all, it's not a droopy line, it's accelerating. And the physics majors know it's accelerating because the slope is increasing. All the physics majors know that. Okay, good. And until we know what the dark energy is, even though we know that we're the universe that's uncurved, until we know what the dark energy is, we can't say anything sensible about the fate of the universe. And in fact, if it's quantum vacuum energy, the universe will keep accelerating. And oh, this is a sad story. So you need to become a cosmologist now. In about 60 billion years, we won't be able to see but a handful of galaxies in the universe. The microwave background, too faint to even detect. So that's why we got to do cosmology right now. We got to spend all the money right now, because in 60 billion years, we won't be able to do it. Okay, what do we got left here? Oh, how did the universe get its lumps? Okay, because remember, it's lumpy. We saw that picture. It's lumpy. Stephen Hawking, people still don't see it. How to get its lumps. So this is one of these big, beautiful ideas that Alan Guth had this idea. Maybe the universe went through a big, big growth spurt. Actually, at the time, he was afraid to say accelerated expansion, but had a growth spurt just like dark energy, and everything got blown up. And in the process, what got blown up were quantum fluctuations on subatomic scales too small to even imagine. They got blown up to astrophysical size, and those quantum fluctuations became the seeds for galaxies. Did you all get that? Yeah, is that a crazy idea? So that is an amazing, crazy idea. And so the microwave background, if that idea is correct, its imprint is left in the microwave background. And these are measurements of the microwave background. I won't tell you quite what they are. The red curve is the theory curve. And you see all the data points. And the red curve goes through all the data points. So that theory might be correct. But actually, another one of the people that Barry brought here, there's a real smoking gun that involves looking at the polarization of the microwave background. That we're not quite done with that story. Okay, what's beyond the observable universe? So I know this is the part everyone was waiting for. What to do about, everybody heard of the multiverse? Okay. How many people think that we live in a multiverse? Because we do everything by opinion polls here, not by evidence, Barry. How many people don't think we live in a? So we have a very sensible, some people hedging their votes here. Okay, so, oops, there we go. So this is the whole story I told you before. Here's the Big Bang. According to Einstein, the Big Bang is the creation of space-time, matter, and energy. Here's the quark soup. Here's where we are today. Universe is getting bigger. You get the wedge here. If you now put inflation in, which is what I was just talking about, you have a universe. Oh, I forgot to tell you something about inflation. This is a little secret. If it happens once, it happens many times. And when a physicist tells you many, you know what that really means. It means an infinite number of times. Okay, so this is the inflationary multiverse. So you've got, this is a Monet painting. Okay, so you're supposed to look at it with your Monet eyes. So this is the river of time. And every once in a while, there's one of these bursts of inflation, and they create one of the wedges I just showed you. And so we're in one of these wedges. And we can test whether or not our wedge came from inflation. But there are other wedges. And so that leads to the inflationary multiverse. Oh, I forgot to tell you, we're going to marry this with string theory. Okay, and if you marry it with string, remember string theory says there's more dimensions out there, and we don't understand why we only have 4. So you might have different bits of the universe with, this is a great story, isn't it? And so some of them are really boring, some of them can evolve like this. So this is a fantastic story. And the story is the universe is much bigger than we could ever imagine. And so there's Barry giving me the stink eye again saying, yeah, but how can you test this? And that's where you get the headache. This is the multiverse headache. Is so those different pieces of the universe don't talk to one another. They can't communicate. So this could be the most important, I put discovery in quotes. I'm required to because it's not made by an instrument. And since Copernicus, and who would bet against the universe being much bigger than we've already seen it being? But we can't test it. So what do we do about it? Okay, I don't know. So you guys have to figure that out, because maybe these little bits, well, they're kind of touching here, but maybe we don't understand the laws of physics well enough and they can communicate with one another. Okay, so we're in the home stretch here. I'm going to finish up. I hope I've convinced you, number one, that we've learned a lot about the universe. And number two, that there are big puzzles left to figure out. And the part I didn't do very well here that I'm going to do right now is kind of an ode to how smart we are. And I really should say the instrumentalists, but I'm going to use the royal we here. It is absolutely amazing that human beings can build the James Webb Space Telescope to see across the universe, to see these galaxies that are 20 billion light years away. What else is amazing? Oh, I put this LIGO. So you guys must know about LIGO, but LIGO is this big instrument, 4 kilometers long. There's 2 of them. And they're looking for the ripples when 2 black holes collide and coalesce. They're looking for the ripples in space-time. And here was the first event that they got. And you can see the curve. They're measuring ripples. They're measuring strain. So 10 to the minus 21 is a small number. But what is strain? Strain is how much things move divided by the 4 kilometers. So the distances that they're measuring with these devices is about 1,000th the size of a proton. Human beings built that instrument that allow them to look and detect that black holes are colliding and coalescing. Oh, we already did the microwave background. We're getting these photons from when the universe was 3. That's amazing that you can build an instrument that does that. And then the last one I put in here, because I like the way that people are looking, we can build instruments that look into the world of subatomic particles and discover the Higgs boson. So we do that in studying the universe. So why does any of this story matter? Why, particularly the story. I mean, if I told you about the technological spin-offs and, you know, that by understanding science and universe and straining to build instruments that are ever more sensitive, so why does this all matter? And I kind of leave that, you know, you can turn that's your homework and you can turn it in. So I didn't put the answer up here. But, you know, First, I mean, I'll give you my answer. It's really fun to try to figure out what happened. And then, you know, the more philosophical, and doesn't everybody wonder why we're, you know, why we're here, how we got here? Is there anyone else here? How does all this work? I mean, it's this, at the end of the day, some of this is not very useful, but it's inspiring. It's fun, it's inspiring. And so I will leave you with that thought, and you know, turn in your homework. Why does all of this matter? Thank you very much.
Okay, thank you very much, Michael. We have time for a few questions.
Oh yeah, now we have to turn up the lights because we don't.
Thank you so much for the amazing talk. I lost one. So the secret of inflation, I lost you there. Why the fact that we have one inflation means that we have multiple inflations? Why?
Oh, say that again. I missed it.
So you said that the fact that we had the one inflation,
one?
inflation.
Oh, one
Thank you.
inflation. Yeah.
Thank you.
Oh, sorry. Yeah.
That's fine.
Got chocolate in my ears. Too much good food out there.
So the fact that we had one inflation means that we had the multiple inflations.
Oh,
Why?
well, the universe is a big place. Yeah, inflation is complicated. So the part that I didn't tell you is that in Alan Guth's idea is a tiny little bit of the universe explodes. Okay, and everything we see comes from this really tiny little bit of the universe. And it was designed to solve some problems. Why is the universe so regular and smooth? And it's because it began from just a tiny little bit. But bear with me here. So here's the universe before inflation. What about next door here? So that could have blown up too. So, and in fact, if you look at the theory, if this one blows up, that one can blow up too. And it gets even more complicated than that. But and this is a wonderful thing about how foggy it is at the front. I think this is Frontiers of Science or something, Frontiers of Cosmology. It's really foggy out there. So we have this idea, which is probably not 100% correct. And it predicted that red curve that went through all the points. But it also seems to say that we live in a multiverse. And one thing I know for sure is the way we talk about inflation today is not the right way. And so maybe it will lose that, you know, maybe 30 years from now, you'll be saying, you know, I went to this lecture by this crazy guy from Chicago. All he kept talking about was Chicago and everything. But I do remember the one stupid part of his lecture was that the multiverse, which is totally ridiculous. It's, you know, inflation, I think he mentioned inflation, but that was absolutely right. But he had all the details wrong. And there isn't a multiverse because that would be silly. And that often happens in science where we get this idea. In fact, Einstein, I'll tell a quick story about Einstein. His first version of general relativity was wrong. It didn't, he said it's going to follow these principles. And a child today could see it didn't follow those principles because it's really foggy out there. Oh, an even bigger one with Einstein was he didn't realize that his equations predicted that the universe was expanding because it's really foggy out there. Thank you for your question. If there's another question, I'll have a shorter answer.
I have a very short one.
That's
Why
not
the
the
moose?
problem. It's the answers are too long.
Why dark matter is a moose?
Oh, why isn't it the moon?
Moose diagram.
Oh, why a moose diagram? Oh, well, that's another thing that tells you why you should be a scientist. So I went to a wonderful meeting in Sweden, sponsored by the Nobel Foundation, at a hunting lodge. And so I had to give a talk about dark matter, and they had like this spread. I mean, that was a really good spread out there, but this spread was, the theme of the spread was many animals of the forest are edible. And so, well, I don't eat red meat, so I didn't eat any of the animals. I ate some of the fish. But one of the Russians was going to go out moose hunting. And he was totally lying. He was just, you know, he had me going. And so I thought, okay, I'm going to make a moose diagram of dark matter. Is that a good version of, it's actually even true.
One more question?
Was it?
Hi, thank you. And my question is very simple. I heard that you say that the universe is expanding. They say that the moon is moving away from Earth like 3 centimeters every year. Is that true? And what will be the consequences for our
Oh,
planet?
so you said the universe is expanding
Uh-huh.
and
And
I-
that the moon is moving away from Earth 3 centimeters every year. Is that true? And what will be the consequence for our planet? If that
can you
is
help me
true.
with the question? I'm still not hearing a key thing. I got the universe is expanding and there's more and
And the
more space.
moon, the moon is moving away from the from Earth.
Yeah,
from-
as the
from our planet.
galaxies are getting further away.
And what will be the consequence from our planet if the moon is moving away and away?
Oh, are the planets moving away? Well, I don't really care about the planets because they're so boring, but no, they're not.
Earth.
No, that's a really good question. So, you know, when you give a talk like this, you have to paint with a broad brush. I left out a lot of details. So galaxies are not expanding. You're not expanding. Atoms are not expanding. And the solar system is not expanding. Why? Because they are big collections of matter. And so there's extra gravity here that holds them together. So in fact, let me just tell you the galaxy story. So our galaxy was expanding before it was a galaxy, but remember there was slightly more matter here. And so that region of the universe expanded more slowly. And then the gravity got stronger and stronger. And eventually that piece of the universe just stopped expanding. So our galaxy, everything in it, you, atoms, not expanding.
So the moon is not moving away from the Earth.
Sorry, what?
Moon is not moving away from
Oh,
Earth.
the moon is moving away from the Earth. You noticed.
Is it true?
Yeah, that's one of my, yes. Oh, was that really the question?
Uh-huh, that's the question.
I'm answering so many different, yeah. So the moon is moving away, and that's a really interesting story. It's moving away. Can anyone help me? Is it a few centimeters a year? I think it's a few
3
centimeters a
centimeters.
year. And is that
What-
right? 3 centimeters. Okay.
What will be the
That's a few.
consequence for our planet?
And
Mhm.
it has to do with the tidal interactions between the Earth and the moon. So it's a local problem.
Yes.
It's a local problem. And it's really interesting because it means in about 40 million years, there won't be any more solar eclipses.
And what will be the consequence for our planet if that, and eventually? If you can answer that, if not, no.
Actually, I missed the last part again. I'm sorry. Oh, for our planet. Well, that's a really good question. None that I know of, because I think the moon is not that important for our planet. But yeah, probably none. But you never want to say never, because a long time ago, we would have said, Jupiter, it's just this big thing out there. It's not important to us. Take Jupiter away. If you have to take a planet away, take Jupiter away. So we know Jupiter is really important to us because it protected us from the debris of the early solar system. And so it swept up all the debris so we weren't constantly bombarded. I don't think the moon does anything like that, but the moon is slowly slipping away and it'll be sad, but nothing lasts forever.
Some time ago, I was talking to you, and you said that you asked Chandrasekhar in Chicago if Einstein had understood general relativity. He said no. Could you elaborate on that?
Oh, can I explain that?
Elaborate. What does he mean? No.
Oh, elaborate. Yeah. So, you know, another one of those plumbers. So Barry's a plumber. And So a friend of mine, Bruce Winstein, asked Chandrasekhar, everybody know, University of Chicago Nobel laureate, one of 100, but not bragging, and asked Chandra, who was an expert on general relativity, how well did Einstein understand general relativity? And Chandra's answer was very poorly. And so Bruce, it took him a while to get it, and then he laughed. And so it's a really deep, deep statement. So it took 100 years. So Einstein discovered general relativity. So, but he found this toy, he found this mathematical structure that took 100 years to understand. And so it took, in round numbers, don't ask me the exact date when we understood everything, but I think now we generally have figured out all the consequences of the equations in general relativity, but early on it was extremely confusing. And so, for example, this has to do with gravity waves and LIGO. Einstein wrote a paper proving that gravity waves weren't real. And he sent it to a journal, and they sent it to a referee, actually a professor at Caltech. And the professor at Caltech pointed out a mistake. So Einstein was incensed. He told the journal, I did not give you permission to send my paper out for review. I sent my paper to you to publish. And so he read what Tolman had to say about the paper and then published it in another journal saying gravity waves are real. And so it's the fog. It's not just in the experimental laboratory. It's even for the smart theorists. It's foggy out there. You know, you get this new thing called general relativity, and it took 100 years to understand what it meant. Black holes. There was a big debate until I think roughly 1960 about whether or not black holes existed, whether or not that solution existed. And so it's really foggy out there. Is that a good enough answer? Yeah.
All right, so I asked one of my friends these two questions, and he gave me a really good response that I don't have the capabilities to understand. But I'll give it to you. One, do you believe in wormholes? And two, do you believe in warp drives?
Oh, well, first of all, I'll give you the simple answer. So scientists don't believe in things. It's all about evidence. But I know you were just speaking in a manner of, but wormholes are a really good example. So that's a prediction. That's something in general relativity that it's basically something that would connect two regions of space. It would be a shortcut. And so it's too bad Kip Thorne is not here because he wrote a book on this and it was in Interstellar. And so we can't prove that wormholes don't exist. But the problem with wormholes is if you try to go in a wormhole, they close up.
Right, it's like infinitely small, right? But I think it's different if it's rotating. Maybe I'm not sure.
Oh, say that again?
I think it's not like infinitely small if it's rotating. Maybe I'm not too sure about the solution though. The particular solution for rotating, it was like by Roy Kerr in 1963 or something.
Oh, the rotating black
Yeah.
holes.
Yeah.
Oh, so black holes, most black holes are rotating. And so the geometry around a black hole is more complicated than the geometry around a regular black hole, but it's not a wormhole.
Right. Okay.
And actually, you're saying, so the simplest wormhole is the black hole that connects two regions of the universe.
Yeah.
I don't think the rotation helps to stabilize it.
Okay.
But we don't know about wormholes, and that's an active area of research in general relativity. Is there a way to make one of these things work so that it could be a practical thing? So I guess when I say we completely understand general relativity, you just found a counterexample that we still need to figure out the wormhole thing.
Okay.
Thank you.
Yeah.
Okay, so I have a question about the Big Rip.
Oh, okay. I love the big rip.
Yeah, what exactly does it mean for space-time to tear, and how is that possible anyway?
Oh, okay. So the big rip, we were talking about how the universe ends. And we talked about if it's vacuum energy, it just keeps, it's a red out. The universe, we just stop seeing galaxies. But a student of mine, a former student of mine, wrote a paper saying maybe the acceleration accelerates. And if it does, space ends in a big rip and everything gets ripped apart. Galaxies get disassembled. You will get, I mean, not picking on you, you will get disassembled. The atoms in your body will get disassembled. And so the universe will end in a singularity. And so singularities are one of the dirty little features of general relativity that make people think that there's a better theory of gravity than general relativity. So let's start out simple. According to Einstein, the Big Bang beginning was a singularity. So do you know what a singularity is?
Not too great of an idea.
So actually, I have a really good example. It's taking 1 and dividing it by 0. So didn't your math teacher tell you you can't do that? And it's not infinity. It doesn't make sense. And so a singularity is where the laws of physics break down. And so if you're a licensed physicist, when you get licensed, you have to, there's a creed that you have to agree to, and that's that the universe everywhere and at all times is governed by a set of rules. So a singularity is a bad thing because that's where the rules break down. And so the Big Bang, according to Einstein, is a singularity. That's why people are looking at alternatives to, or something that would complete the Big Bang called string theory. And if there's a big rip, it's the same kind of problem, but in the future is that space-time gets, instead of infinitely small, it gets infinitely big. And it's a singularity. The laws of physics break down. So that, if you're a licensed physicist, you can't believe that that's the answer. You think there's something better. But the big rip is one possibility, that the acceleration accelerates.
Thank you.
I think we're done.
I think we've exhausted questions, so let's thank Michael. Thank you.